Hey guys, we started the stream. Let's check.
Hey guys.
Yeah, I'm live. Okay, great. So, welcome back to another video of one of the most popular series in my YouTube channel. Also because it's the only one. Let's keep working on what we were working yesterday. So we were working on educative. Yesterday we focused mainly on tries. Today let's go with the graph, which is next section. Again, if you wanna start learning from educative, you can go to the site. You need to pay a subscription. The course I'm currently doing is called Ace the Python Code Interview. So I've done most of the topics in the first module. So and today we are gonna do something something related to graph. So let's go. Let's start from challenge 1. Okay. In the meantime, I will open the studio code and publish. So I'll zoom a bit. Okay, let's go. So first challenge is implement breadth first search. So your solution should work for both connected and unconnected graph. Anyway, problem statement. You have to implement the breadth first search traversal in Python. We have already covered the logic behind this algorithm, and all that's left to do is to flesh it out in code. Okay, let's even skip this one. The only thing I'm gonna check now is how we define a graph, because that's the main part here. I think we have the class. We have node. Okay. We have also graph. Each graph can have multiple vertices. We have add edge. Yeah, it's so bad this. Okay. Anyway, the idea of a graph, actually what is a graph? A graph is a collection of nodes, and each node can have multiple connections to other nodes in the graph. So this can be represented in two ways. A graph usually can be represented in two ways. The first one is through agency matrix. So you have a matrix which represents the connection between the nodes, and between and also another way to represent a graph is the neighborhood list. So instead of having a matrix which represents the connection between each pair of nodes, you have for each node an array list, a linked list, whatever, that where you store the connection to another node. So in general, when you implement a breadth first search in a graph, the idea is that you will you will touch all the possible nodes in the graph. So first of all, we need to define the graph, and in order to do it, we have to create a class node, I guess, see anyway here what it does. It create a graph. For a graph, you have vertex, and for each you specify the number of vertex. and you create array dot append, and for each vertex you add append a linked list. Nice. And actually what you do, in order that when you add an edge, you give source and destination, and you add to the array of the source is a connection to the destination. Well, pretty bad. I don't really like it. I think, well, I mean, it makes sense, but I think we will do our own implementation. So, first of all, let's create a file. We will call it bps graph.py. So, every time I create a new script, usually I do this, def main, and this is gonna be the main function where we are gonna create the graph and vertices, and also here we are gonna invoke the function to do the breadth first search. In general, in Python, in order to invoke the main function from command line, when you execute the script, you do this, something like this. Okay, nice. And you invoke main. So here, the idea, the skeleton of the main is going to be a graph. So we're going to create a graph. And actually, we don't even need a graph. We don't even need a graph. We just need a collection of nodes, no? And we just need a node, which is the root. That's it. We don't need to create a specific class for the graph itself. So I would say that we define the root. So let's keep it simple, also because in coding interviews, you have to be able to do what they ask you in the current file from scratch. So as simple as you can keep it, it's the better, because in this way you can really show that you can implement whatever you want. You just need an empty file. So we will need a root. This root will have a name. We could use string or numbers. Let's go for numbers. So we will have root. The root node is one, and we could do root dot append add neighbor. Add neighbor, and we can pass another node here, no? So the idea is that we will create a bunch of nodes. Let's do like this: node 1, node 2, etc. No? Not 4, not 5, not 6, not 7, not 8. Okay, 1, 2, 3, 4. Okay. So we are going to do 3, 4, 5, 6, 7, 8. Let's go for 10. Let's go for 10. 9, 9, and let's go for maybe so much 10, but yeah, it's okay. So node 0. Okay, let's create a class node. Graph init self data equal data. Okay, and we are gonna have self.neighbors equal empty list for now. And we are gonna have a sort of a method which we will call add neighbor, where you take, which is a method of the class, and it's gonna take as an input the neighbor node, no? This So what it does, it just self dot neighbors dot append and we will put a pointer pointing to the neighbor node. So in this way we are appending, so we are adding to the list of neighbors the reference to the neighbor node. So let's try to draw our graph. How can I draw the graph? I can use draw.io. So you can see it from drawer.io. Now what I'm gonna do, create a new graph. I'm gonna really draw the graph. BFS. Save. Okay. So the idea is this. Let's take a circle. So we have one. Okay. Okay. 18. Good. 18. Again. Okay. So we have node 1. Let's do something simple. No? Let's even reduce the number on node 2. We are gonna have 3. We are gonna have 4. And we are gonna have 5. Nice. So the idea is that we are gonna create, we are gonna connect. Let's assume that our graph is as oriented connection. So it means that I can go from 1 to 2, for example, but I cannot go from 2 to 1, no? So in case I want to go from 2 to 1, I have to add another arrow that starts from 2 and goes to 1. So let's assume we don't do this. So let's assume that this is like we connect from 1 I can go to 2 and not vice versa, okay? So let's go from here, from 2 we can go to 3, from 2 I can go to 4, for example, and from 4 and 3 I can go to 5, okay? So starting from the root, I can reach any node, no, in the graph. Easy peasy. Okay, so let's go and write the code to create this type of graph, no? So the node 0, let's remove node 0. Let's keep node from 1 to 5, okay? So node 1 will have only one connection to 2. Node 2 will have 2 connections, one to node 3 and one to node 4. Node 3 will have one connection to node 5. And node 4 will have one connection to node 5. So this is the representation of our graph in code. So assuming we have a BFS method that we are going to implement, we have to pass the root node, so the starting node where we start, and in this case is node 1, okay? but it could be any node at this point. So let's go to BFS. Let's go to implement BFS. As you can see, BFS is just a function itself, is not a method of the class node. It could be even a method of the class, starting from the node, from that specific instance of the node. We could do something like that. I mean, we can even pass it in input. So let's go in this way. So by default, I would always define the edge case. In this case, is if root is equal none. So if root is equal none, we just return none. That's it. Pretty straightforward. So otherwise, in general, BFS when you implement BFS, you need to do this. This is the queue of Python from collection import DQ. So the idea is this, that we define a queue, and in this queue we add the root node, no? Nice. Easy, no? Once we added the root node, the idea is that we are gonna keep popping out elements from the queue until they run out, and in this way we iterate through all the nodes in the graph. But every time we pop out a node, we just push in the queue the children of this node, the neighbors of this node. In this way, we will keep adding elements to the queue until there are elements which we didn't visit. But we have to remember one thing: we have to keep track of which elements we are visiting, because this is pretty easy to understand. Because it could be that, for example, let's go back to our graph. If I have something like this. If I have a connection between the 5, for example, and the 2, it could happen that once I arrive to the 5th node, the 5th node has one neighbor in his list, which is 2. And if I go to 2, which I visited already, I could, get stuck in the loop. So in order to avoid this, we have to keep track of the visited node. How do we do that? We add a flag to each node. In this way, we understand if the node has been visited or not. So let's go to implement this here. Visited equal false by default. Okay. So back to our BFS. Let's go here and we do len of q. So if the q is not empty, so if len of q is more than 0, we keep staying here. So we get the len of q, which is silent. So, and this tells us how many nodes are in the queue at this current iteration. So we do for e in range of size. And we pop out q dot pop left current node. So the current node, usually what we are going to do here, we are going to print, I think that what makes sense here, be anything, current node.data, and we are gonna set the flag visited to true. So once we have done this, we have to check for all the neighbor of this node and check if we can add them to the queue. So we go for a neighbor in current node dot name neighbors. Okay, current node dot neighbors. If neighbor dot visited is false, equal false, then we do q dot append neighbor. Okay, and we keep going until we finish. Actually, we don't even need this. I don't know why I did this. So this should work now. Let's try. So 1, 2, 3, 4, 5, 5. Why this is happening? Because the visited node, maybe the why, as you can see now in the output, we have 1, 2, 3, 4, 5, and 5 again. This is pretty annoying. Because what happened here? What happened that with that neighbor node 5, they are both pointing to node 5. If node 5, wait, okay. I think I know what's going on. Let me debug. So we have to neighbor dot add. So we are now at 2. Okay, let's go. We are at 3. Okay, let's go. We are at 3 again. Let me check again. So this is the graph we have now. Because no, actually what they want is current node. Okay. So we have 1, okay. 1, we start from 1. We have 2. Okay, we are at 2. Let's go. We are still at 2. Okay, because I'm stopping here. Maybe it's better to stop. We are outside of the floor. So let's try again. So 4 neighborhood and current node neighbors. Nice. So if we do current node dot data, we are 1. We are in the 1 node. Okay. Now we are in the 2 node. Okay. Okay. Now we should be in the 3. Okay. So now we are at the 3rd node. So in the 3rd node, we have current node dot data, which is 3. Nice. So if we do current node dot neighbors, we have a list of 1 neighbor, which is node 5. If we go, this is what I'm interested actually. So you see, if I go up, if I check the data of this, we have 5. So that makes sense, no? That's what our node 5. So let's go, continue, and let's see which is the next one. So 4. Let's check which are the neighbors of 4. See, is the same node because the reference object is the same. So if I do neighbors 0 dot data, I should see 5. Okay, but in this case, the visited is false. Makes sense. Now I understand. So if I check Q, no, Q is quit in the PDB. Anyway, I understood what is the problem. The problem here is that we are putting 2 times the neighbor which we visited already. So because at that point in time we didn't visit it, so we are printing this 2 times. Why? Anyway, here well, I think we have to store it. We have to also add another variable which is in the queue. Which is by default false, and when we add it to the actually we should check this one in the queue if we want to append it. And set it to true. So in this way, we should be fine. Instead of doing it like this, maybe we don't even need the visitor, I guess. Yeah. So was the error. Actually, we have to, the flag is not useful to check if we have visited or not. The flag is useful to understand if has been already put if the node has been already put in the queue. In this way, we know if it was already in the queue or not. So that's how we implement DFS for a directed graph. So let's go to the next question. I assume this is done. So this algo, actually, we could even discuss the computational cost of this. The computational cost of this should be the number of edges we have actually the number of node we have. Yes, the number of node we have. No, the number of edges. The number of edges, I'm saying the number of edges is the key factor here, because every time we do a for where we check the neighbors of each node, and this takes and this actually is the heavy part. So it will take O, big O, of how many edges we have in the graph. That's what it takes to do BFS in a graph. So let's go to that's what actually is the heaviest, because it could even be, no, actually is the number of edges plus the number of vertices. So it's how many vertices we have plus how many edges we have. That's the total computational cost of that. So implement depth first search. So let's go with depth first search, which is pretty different compared to breadth first search. Breadth first search goes layer by layer. So first we check one node and its neighbors, and after the neighbors of the neighbors, and after the neighbors of the neighbors of the neighbors, etc. Instead, when we do depth first search, first we take a node and we go to one of his neighbor, and after we go to the neighbor, one of the neighbor of this node, and later we go to a neighbor of a neighbor of the starting node, etc. And in this way, first we go in depth, and after, so we don't check all the neighbors of a given node, but we go in depth to the farthest. Well, to the most far node we have from the starting node. Anyway, so let's go. BFS. So we are going to implement DFS. DFS actually, when you have to implement, when someone asks you, hey, you need to implement the DFS. DFS usually is a recursive. So you have to call the function itself. I can start to implement DFS from here, from the same function. So with the same idea. So first of all, we check if the root is equal none. In case it's none, we just return a none. Otherwise, what we do? We do the following. Starting from the node, we go here I do like this, because here we will have the flag which is dirty. So in case we run first BFS, we will not have the flag which is in the queue. The flag in the queue will be set to true. So doesn't work for us. So DFS. So the idea of DFS, first of all, we print the data, and later we go to all the neighbors of root for in root dot neighbors and we do the fx of and we do it only if neighbor dot here we call this flag is in the queue. Let's recall it visited. So if neighbor visited is equal false, then we go with the DFS. Otherwise, we don't need to do it. And we have to do also this one. So you go down, yeah, should be this one. Let's go. Let's test it. 1, 2, 3, 5, 4. Okay. So you see now the output is different. Instead of doing 1, 2, 3, 4, 5, we go 1, 2, 3, 5, 4. Let's check why. So let's go back to our graph. So the FS how it works. First we go to 1 and after we go to 2 because 1 has only 1 children. So we go to 2 and after from 2 we go to 3. No? But from 2 we don't go after 3 we don't go to 4. We go from 2 to 3 and from 3 to 5. And after we draw back. Backtracking. So this is backtracking. And we come back to the 2. Here we left in the stack the function that was called using 2. And after we invoke the same function on 4. So for this reason you see 1, 2, 3, 5 and 4 later. See? That's the reason why. So that's it. That's DFS. Let's go to mark it as completed. So next one is detect cycle in a direct graph. Okay, so how do we detect cycles in a direct graph? Again, first of all, we have to create a graph with a cycle. In order to create a graph with a cycle, instead of, for example, doing something like this, 1, 2, 3, 4, 1, 2, 3, 5, 4, we could do something like this. We could do something like this. Okay. We could do something that 1, 2, 3, we go from 1 to 2, from 2 to 3, from 3 to 4, and from 4 to 5, and from 5 we go back to 3. So in this way we created a cycle, no? Let's go and try to write an algorithm that is able to detect if there is a cycle in a graph like this. So the idea is that from node 1 we go to node 2, from node 2 we go to node 3, from node 3 we go to node 4, from node 4 we go to node 5, from node 5 we go to node 2 again. Okay. So the detect loops, actually, how it works. When we have a loop, the idea is that we have a loop every time we visit a node that has been already visited. Pretty easy as that, no? Oh well, no, that's wrong. That's wrong because, for example, in the case that we had before, we were visiting 5 2 times, but that there was no cycle, no, there. How do we do that? Let's go and check it. Mm, mm. So educative helps you also to understand this. So when you don't know something, you forget something, you can go check the solution. Well, I'm confusing, but the logic is pretty straightforward. For each node, we start a recursive call with the function maintain a stack, not to be confused with the stack data set of nodes. Need a visited list. The vertices that have been traversed in the current recursion are added to the list. The nodes. The vertices that have been traversed in the current recursion are added to rec node stack and visited. Keeps a record of all the nodes that have been traversed, regardless of the recursive call. Regardless of the recursive call. So for a cycle to occur, we must reach a node that was already present in the recursion stack. If the recursion ends and no such node is found, the stack is reset again, and the next iteration of the tech cycle starts. So he uses the stack. So the idea is that when we go and we find that a node has been already we have already a node in the stack, this means that there is a loop. Let me think. It should be visited. If it's visited, talk is cheap. Let's show me the code. Let's see. Detect cycle. Okay. So it's if it finds for a given stack, so it stores all the nodes in the stack, and if it finds again the same node, yes. I mean, I hope there's something more elegant, but I think we cannot do. This is the best we can do. So let's go implement it in this way. I will implement it my own way. So my suggestion is always, if you don't know something, check the solution. That's there is not much you can do if you cannot come up with a proper solution. But later, let's try to do it by yourself. Also because otherwise you will never understand. Like if you just copy paste the code, doesn't make sense. So detect loops. Detect loops. First of all, we are gonna have the root. No, the root. Let's do it dirty for now, and later we'll see if we can improve it. Okay. So the idea is that we are gonna use we could use DFS, so we are gonna copy paste the DFS, but detect loops instead it will have the root node, but it will have also the a stack, which is an empty thing, which is an empty array, no? So every time we visit something, we add it to the stack dot append, no, with root dot data, and after we call the neighbor here, and we pass the stack. But here we do a check, so we do a stack.append root data. When we print, you can even put this, but what we are gonna do here before we print it, we check if if root.date is in stack. So if this is true, we found a loop, so return true. Otherwise, we keep going and we just return false. Let's try. Stuck. Wait, I need to print out the detect loops result. That's wrong. Is equal true. In that case, we just return true. False. Because equal false, but no, this actually we don't need this. true. Okay. Let's try to create another set case. So in this way, we created detect loops, but let's check if we, instead of doing node 5, we just remove this. This should return false, indeed. So, and if we, for example, we go node 4 pointing to node 1, also this one should detect a loop. And if we go, for example, we leave it like this and we do node 1 to node 1. True, yes, because node 1 is pointing to itself. So the problem here, I think, is that we are not unloading the stack. So still it doesn't really do what it's supposed to. Stack.append. Stack, you just append that. And cause stack, okay, you add it. And you return a true. But here, before we get out, we have to delete the stack position and of stack -1. Same here. So before we get out, we have to delete it. Wait, how it's the deal? Deal in icon. We could just pop it, guys. Fuck. For this reason, we use the stack. Okay, so this is true because we have 1. Nice. So this should be false. Okay, and here should be true again. Yes. So did you understand what I did? I just popped out from the stack a given the element the current element. So in this way, when we return to the previous level, so we return true or we return false, the stack list will not have the element. So in this way, the stack is always updated. In order to double check this, we could do something like this: print stack each time. So we have 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay, in this case it doesn't really work. Node 5, other neighbors. Node 5, node 2. Okay, we need to do something like this. So 1, 2, 3. See, you do 1, 2, 3, 4. You go to 6. Fuck, I have one. I wanna see the 6 nodes. So we do node 7, node 7. See, so you go 1, 2, 3, 4, 5. 1, 2, 3, 4, 6. You go to 6, and after it gets removed because it goes to 5. So in this way the stack works. If I gonna remove the stack.pop, you will see that something will not work as it should. See, the stack keeps stays dirty because we don't remove the 6, for example, neither the 7th. So instead, if I do stack.pop, this doesn't happen, and the stack is always clean. So yeah, nice. Now, so we have done three challenges related to graphs, which were pretty good. Tomorrow we will go through the others. As you can see, many challenges are related to graphs, but yeah, for today I think is enough. Thank you so much. Please share and subscribe, and leave a thumbs up if you like the video. That's it. Thank you so much, guys. See you next time.